shall we begin?
So welcome to the third day of the talk. And so our first speaker will be Roman, talking about the experimental signatures of Majorana modes and quantum computing. Thanks.
Morning, guys. Today I'll just start right away from this experiment that I outlined last lecture, during last lecture. This is zero bias tunneling experiment, and I'll cover basically experimental signatures, and I'll talk about quantum computing and how to basically supplement these topological, in other words, very precise quantum gates that one has from braiding of these Majoranas with some other gates to get a universal quantum computer. Okay, so as I mentioned last time, over the last couple of years, there has been enormous progress, experimental progress in this direction, and there were 5 experiments on zero bias using different structures, using indium arsenide and indium antimony nanowires placed in superconductor, and all of them see zero bias signature in finite magnetic field. And then there is also an attempt to measure Josephson effect, very special Josephson effect. It's called fractional AC Josephson effect, which I will explain later. Okay, so as Professor Yazdani yesterday emphasized that whenever we are measuring zero bias peak, one has to be careful and one has to exclude possible other explanations. And there are many possible other explanations, including this reflectionless tunneling, and disorder, and conduct. So let's start with zero bias tunneling conductance. Again, this is a setup, a nanowire placed on top of the superconductor. There is in-plane field, and we're trying to tunnel into the end of the wire. And we're trying to probe the spectrum, basically density of states of the nanowire. And as I showed you yesterday, it changes across the phase transition. So this is exactly what you would like to understand, whether the zeros order model checks out. Okay, so if the system is in a topological regime, then you should be measuring something like 2 square of h. If the system is in non-topological regime, then close to zero bias, at zero temperature, you should be measuring something close to 0. And that can be understood from this Andreev reflection phenomenon. So you have incoming hole, incoming electron, which is reflected as outgoing hole, and the charge is transmitted in superconductor. But if this electron is incoming with 0 energy, and there is a state at 0 energy here, there is a so-called resonant Andreev process, which means that this Andreev process has unit probability. So there is no normal reflection, which would be an electron coming in and backscattering back as an electron, but everything goes through this Andreev process. So normally when we want to compute current, this is the expression. So you have Fermi functions, and they're sandwiched with the probability of for particle hole process. So this is the square of the particle hole component of the scattering matrix, which one calculates at this interface, and then compute the zero bias conductance. So
what does N and S stand for in the end frame?
N is a normal metal, and S is a superconductor.
So N is like your tip of your...
Just the Fermi. Yeah, so that's the tip in that picture. Just, yeah, because the tip is normal, and S is a superconductor.
What is gamma in the axis?
Okay, so the gamma is basically the coupling between the normal metal and the superconductor. So if you don't have Majorana, but suppose you have the system and another N, right? There is some matrix element, there is some coupling which characterizes the interface here, and that's scale gamma. Okay, so as I was saying that if you are looking at the scattering matrix at zero energy, it only comes into, it is heavily constrained by the unitarity and particle-Hall symmetry, and therefore there are just two choices that we have. And these two choices, they correspond to complete normal reflection, so meaning that electron comes in and backscatters completely as an electron, or complete Andreev reflection process where you have electron coming in and it backscatters as a whole with a unit probability. So, and I will explain later today that these two scattering matrices actually correspond to two different boundary conditions that sort of Majorana imposes on the lead electrons. Yes, questions?
Yes, on the figure on the left, is normal, does it mean that tip and superconductor is the bulk superconductor, or? I'm wondering what, so this scattering matrix, is it for the wire or something else?
This is a scattering matrix obtained for this interface here. So you're trying to match the boundary conditions at this interface and obtain
which interface is it?
no, NS, normal metal S. So suppose you have, forget about this tip picture, but you have a picture, you have a system where you have normal metal coupled to a superconductor. Then generically, if you want to understand what happens at this interface, you just define a scattering matrix, so which is a scattering matrix from N to S, right?
And the superconductor here is the bulk superconductor.
Yeah, it's a bulk superconductor.
So this scattering matrix contains all the information of the wire?
Yes.
Okay.
The scattering matrix contains some information of the superconductor, but in certain approximations, which you're going to make, where the gap is large, basically one uses a so-called Andreev approximation, where we neglect the time that electrons spend in the superconductor. Okay, I'm going a little bit more technical here, but in reality, what happens that one electron tunnels in superconductor, and then spends some time, and this time is inverse of delta minus 1. Okay, and then there is another electron coming in, and they combine and form a Cooper pair, and then they propagate further. But if I assume that this time, delta minus 1, is very short, I can write an approximate model where basically I neglect this time, and therefore this happens instantaneously through this Andreev process. So does it answer your question?
Yeah, I think so.
Okay. Yes, no.
What's that? You may have said this already, but what's that S, PH or P?
It's a scattering matrix. So basically, it tells you how incoming, plane waves get reflected as particles. So basically, like imagine you have impurity, there is incoming plane wave and gets reflected. But in this system, because charge is not conserved on superconductor, there is additional component, which is a Hall component. So normally, if you have a metal, right, in an impurity in the metal, then particle gets reflected as a particle, right? There is no conversion from particle to Hall. So superconductors are special because they break particle conservation, and therefore particle can get reflected as a Hall. And that's so the scattering matrix that you have to write has a form which describes how particles scatter to particles, then has a form how holes scatter to holes, right? And this is in the case of a normal metal, impurity in normal metal, this would be just a diagonal matrix, right? But now we have this additional component, SPH, and SPH describes the scattering from particles to holes. And so it turns out the expression for the current in this system, since only 2e electrons can propagate in superconductor, right? So unpaired electrons cannot propagate in a superconductor. the process which is given by this Andreev reflection only contributes to the current. Okay, so that's the story, and therefore, if we are using some kind of tunneling experiment, we should be able to detect whether there is a zero bias peak or not. So also, it's easy to work out the details because experiments are done at finite temperature and finite voltage, and so one can compute what happens when in different limits. So at zero temperature, we have two different limits, and the limit we are considering here is when the voltage is much smaller than this broadening, and the broadening, as I said, is a coupling, characteristic coupling that couples between lead and superconductor, right? So the coupling to Majorana mode.
Yes. So if the electrons are coming in at certain energy, which is in the
Yeah.
gap, then there are no energy states to accept that electron, and so where does it spend time? You said the electron is accepted, it spends time somewhere, and then another electron comes in and they form a pair.
Yeah.
So if there are no energy states in the gap,
So you see, the particle Hall formalism basically gives you some symmetry between the energy of E and minus E, right?
Yeah.
So I was saying that when you consider Bogoliubov-Druzhyan equation, there is a relationship between particles at energy E and holes at energy of minus E. So that's why this picture has E coming in and minus E coming out, right?
Yeah.
So in some sense, you add E and minus E and you get to zero. So therefore, Cooper pair is like sitting at the zero at the chemical potential level, and the energy doesn't go anywhere, right? I'm not sure. Can you repeat maybe your question? So I'm not sure I'm answering your question, but maybe.
So I thought you were saying that the physical picture is something like electron is accepted at certain energy, and then it spends some time. So I'm supposing that.
Oh,
at the
okay.
there
So
must be an
actually,
energy level, right?
okay. Actually, electron tunnels into a virtual state. So it's not a real state; it's a virtual state, right? An electron in a virtual state can stay for the uncertainty time. And the uncertainty time is, you just have delta minus 1 is the gap. So uncertainty time is inverse proportional to the gap. So it can stay in the superconductor for this time, delta minus 1, h bar over delta. And it's waiting for another electron to come in. And then when they come in, they just combine and form a Cooper pair and then propagate further. So it's not like it tunnels to some finite state in the superconductor. It tunnels into a virtual state. So in some sense, this is a second order process, right? So if you were to do perturbation theory, that's going to be a second order process. So direct tunneling is not allowed, but if you're tunneling in pairs, then that's fine. Okay. And we do assume that the superconductor is bulk, and so there are some relaxation times, and they are very fast. So therefore, the system equilibrates very quickly. Any other questions? Okay. So, I wanted to show you that. Well, this is our motivation to look at this zero bias tunneling experiment, and I want to show you the experimental data, and then we compare and we see whether things check out or not. So the first picture is a picture from Delft experiment, the Leo components group. So you see there is indium antimony nanowire, which is covered to niobium titanium nitride, a superconductor, S-wave superconductor. The choice of the superconductor was determined basically by the field. So this superconductor is particularly robust against magnetic field. It can sustain the field of order 10 Tesla. And then this electrode is a gold electrode, so this is my N, then there is some nanowire, and this is S. This is effectively like, semiconductor nanowire covered by a superconductor, so this is our model for this topological Kitaev Majorana wire. And then underneath this blue, you have a set of gates, and these set of gates, they do the following. So these gates, they're supposed to change density in the nanowire, and this gate right here is controlling the barrier between normal metal and the nanowire.
Is there a reason why the superconductor covers one side of the wire?
Yes, so the reason the superconductor covers only one side of the wire because is the following. So if you cover a wire entirely with a superconductor, it's going to be harder to tune the density. Basically, superconductor is a big metal, essentially, and it screens very well electric fields, right? So, so the goal is to find some kind of optimum here, induce enough of proximity effect, but at the same time allow the possibility to tune the density in the wire. That's one issue, and the other issue is that we were trying to induce Rashba coupling in the wire. And Rashba coupling appears whenever you have a symmetry at the interface, whenever you have electric field. So this structure, since it breaks the symmetry also, it will also help to have a larger Rashba coupling. Yes.
So in your model, you had a normal metal with a superconductor. Now there's a semiconductor in.
Yes, there is a semiconductor. So this will lead to some differences, and I will explain these differences. So it's not exactly what we have, but if this region is small enough, right, then you can probably neglect. Maybe one can neglect the presence of this region, but it's a good observation, and I'll discuss what might happen in that region.
So what's the reason for building it this
Oh,
way?
it's just it's very hard to, create to place these two materials within this short distance. In reality, this is not very long distance. It's maybe 100 nanometers, a few hundred nanometers. So it's a really really tiny region, and also since you want to create a barrier here, if you put these two metals too close to the barrier, they will also screen the the gate. So you don't want to have that. So there are some geometrical constraints and reasons to do it. Okay, so that's one of the experiments, and there was another set of experiments which involve indium arsenide nanowires. So this is indium arsenide nanowire. Again, this is gold, and this is aluminum, and there are some gates underneath. During this talk, I will mostly talk about this experiment. Let me remind you that indium antimony is a very interesting material, has a huge G factor. G factor is of order 50. So the difference between the G factor in the superconductor and this indium antimony nanowire is 25. Therefore, the fields that they will apply to drive the system in this topological regime are fairly low, and they will not affect the superconductor. Okay, so this is experimental data. This is what they measure. So you can see tunneling conductance, differential tunneling conductance, as a function of the voltage bias. And all these slices here, they correspond to different magnetic fields. So we're changing the field from 0 to half a Tesla, essentially. Okay. So several things you can notice. Well, these are coherence peaks. That's basically, these are the peaks that represent induced gap in the nanowire, induced superconducting gap in the nanowire. Then there is a zero bias peak, which appears somewhere here, roughly around 100 millitesla, and stays at 0 for a very long time, and then gets split into two peaks. then there is this background density of states in the experiment. So now, just for reference, I wanted to show you what the theory predicted. So this experiment was done in 2012, and this theory appeared in 2011. So what we were predicting that, well, you will have zero bias peak, which will be stuck at zero for long distances. And then if you go up, we just didn't go far enough, this peak is going to split. And so that would correspond to this one. But you see there are several qualitative features. So first of all, the density of states does not have the soft gap, like shown here. And second of all, the theory predicts that, well, there should be gap closing at the phase transition. And you don't see this gap closing in the phase transition. So these are the differences. These differences can be explained, but let me just also provide an experimental explanation. This is just one set of data. In fact, they have tons of data, and this is a summary of their experimental findings. So first of all, they have high mobility, quasi-ballistic indium antimony nanowires. These nanowires, the active part of the nanowire was roughly of a few microns, and the mean free pass in these systems without depositing superconductor and everything was about 300 nanometers. So really, there are very few impurities in the system. It's fairly pure wire. These wires are fairly pure. Now, they also can characterize these wires before placing any superconductors on top, and they measure the spin orbit coupling strengths, effective mass, the G factor, etc. And so from their estimates based on these parameters, they concluded that B of the order of 100 millitesla roughly corresponds to this energy, Zeeman energy, 150 micro EVs, which is comparable to the induced gap. So the point where this zero bias feature appears roughly is in the right parameter regime for the topological phase transition. As I said, it remains stuck. It also resists for large gate ranges, so they changed these gates beneath the nanowire, and the zero bias feature does not move away from zero as one tunes the density and other parameters. So it seems like it's very robust, and it's not just fine-tuned by some gates. It actually is stuck to zero. This is very important observation that the zero bias peak vanishes when the field is aligned with the spin orbit direction. So as I emphasized during last lecture, that in order to open up a gap in the spectrum, one has to have a spin orbit direction and Zeeman direction to be perpendicular, right? So that the two Pauli matrices do not commute. And when they do not commute, we have a gap in the spectrum. So since one can rotate the direction of the magnetic field in plane, one can find these directions where the direction of Zeeman coupling is along the direction of the spin orbit field, and therefore there shouldn't be any gap in the spectrum. And so what this statement tells you that, well, for some directions, they don't see the zero bias peak. So they don't see, it basically disappears for some directions, and presumably disappears because the alignment of the field is such that there is no gap opening. And also they check that this feature disappears when you have just purely normal metal, nanowire, normal metal devices. And that should indicate that it also, that it is a signature of superconductivity, a superconducting state. So it disappears when superconductor goes normal. So that's these are the sort of observations that are in line with Majorana explanation. But there are also some issues, and as I said, there is a soft gap issue, and another issue is quantization of the conductance. So at zero temperature, I mentioned that topological phase will have 2e squared over h conductance. And it's a fairly remarkable result that you have a system, there is some tunneling from one subsystem to other subsystem, but the result does not depend on the details. It's just proportional to fundamental constants. And so one should be able to see that in the experiment. And as you can see here, the peak is not actually 2e squared over h. It's not quantized. It actually varies a little bit as you go from here to here. So you would like to explain these two features and try to understand, well, how should we think about the soft gap, and maybe quantization of the conductance, how robust it is to other effects such as interactions and other things. Maybe once you add these interactions, maybe it's not quantized anymore. So we should address this question. But
what about a higher temperature?
Well, temperature corrections will be there, but temperature corrections they can take into account because they can do interpolation, and they can map out how things depend on temperature and voltage, and fine. Even with this interpolation, it's still not quantized. Okay, so let's just try to understand a simple thing, structure which involves N and S system. Actually, this system NS has been studied very long time ago, and there is a well-defined theory which allows you to understand what happens in NS structures. It's called Btk theory, Blonder, Tinkham, and Klapik theory. And this theory studies a simple model where you have delta function-like potential between normal metal and a superconductor, and there is some strengths of this delta function potential which defines this number z. Okay. So there is this number z. Z being very large means that the barrier is very high, okay, and states do not penetrate through this barrier, so it's weak tunneling regime. And z being equal to 0 is a strong tunneling regime. It means that states hybridize quite a bit. So I wanted to emphasize that actually this measurement is supposed to measure density of states only in the weak tunneling regime. Okay, that's very important. So only when we are in the weak tunneling regime, we are just a little bit perturbing the system to probe the density of states in the superconductor. But when the tunneling is strong, then we are probing something else actually. And as you can see, this is for the same superconductor, depending on Z, this measurement would tell me that, well, first there is some filling of the states below the gap. So this is a gap scale. So EV is measured in terms of delta. So there is some filling of the in-gap states. And eventually, when Z is very, very small, we reach some universal value, which is 2 per spin, I guess. And so it's completely independent of the density of states in the superconductor for in this parameter regime. So it's important to see whether the conditions that the conditions in the experiment satisfy this requirement. Okay. So the experimental situation is actually slightly more complicated than I was presenting in the previous lecture, because you don't have just a single subband in the nanowire. Most likely one has many of them. Okay, and it turns out that it doesn't really matter as long as there is an odd number of subbands in the nanowire. It doesn't matter for the appearance of the zero bias peak, but it does affect some other properties. And in particular, I believe it should affect the tunneling conductance, and should affect for the following reasons. So this is a sort of the spectrum of this nanowire without any, say, superconductor, and we are considering here certain widths of the nanowire and certain chemical potential, so that we have a few subbands in the nanowire. So see, 0 is the position of my chemical potential, and I consider that there are 3 subbands. Each of them have a tiny, well, on this scale, tiny spin orbit coupling, right? It turns out that the Majorana physics comes entirely from this subband. It's right here. And these other ones, you would say, well, they're just inert, so they're, participating. They are well below the gap, and they are just inert subbands. But it's important it becomes important when we consider this potential barrier, right? So because different subbands, they have different transmission probabilities through this barrier, okay? And the rule of thumb is that, well, subbands with large k vector, kf, they will have higher transmission probability, and that's because they have just higher velocity, right? High kf means that there is a higher velocity. The higher the velocity, the more likely the electrons will penetrate through the barrier. And so we have to consider a system where the states in the system have very different, vastly different transmission probabilities. And so my point is that for these bands, these subbands, we might be in this regime, or this regime. We don't know. Whereas for Majorana subband, we might be in this regime because it has very low velocity. And in fact, that's basically what we see. We come up with some scenario for some parameter regime where we show that, in fact, the presence of these other subbands might be important for this soft gap issue. So you see, on this plot, there is di, dv, and these are, for example, for one band, this is the picture, this black line. It's 0 temperature result, and the red line is broadened result at some finite temperature. And you can see, 0 bias peak, and then very, very nice subgap, and some sharp features correspond to some discrete state in this model. But this yellow kind of, this red line with yellow background corresponds to having 2 subbands. And in fact, one of them for parameter regimes that we used is in this regime where it's highly transparent. And so you see there is some superposition of the 0 bias peak on top of the soft background, which comes from the other subband. So bottom line, I think one of the possible explanation for the experiment, for the soft gap issue, that is the presence of multiple subbands. Well, another explanation actually is disorder. So if you making an interface between very clean nanowire and an S-wave superconductor, this interface might have some roughness. And so this roughness will create some subgap states in the nanowire. And these subgap states, when they couple to a normal metal, they will be broadened and they will contribute to this background. So I would say there are 2 contributions to the soft gap. One is intrinsic contribution, and it happens in pristine model. And I think that this comes from this multi-band scenario. And the other one is sort of extrinsic contribution, which comes from disorder and other effects present in the nanowire. So there is some evidence that actually this is the case. So these new experiments, they show that one can reduce the soft gap issue quite substantially by making these interfaces very smooth and by optimizing the structures. So the new structures actually show much better data, but they're not published, so I cannot show anything here.
Excuse me?
Yes.
Did you say again what the soft gap issue is?
So yeah, soft gap issue is that, well, normally what we would expect to see is something like that. That's S-wave density of states and some peak in the middle, which corresponds to 0 bias peak. But instead, what we see is something like this, right? There's some peak. So there is no hard gap in this region, but instead it's filled by some states. And you're trying to understand what's the origin for these states. Why is it filled? So one explanation could have been, well, it's just disorder. right? So disorder fills on, like I was showing you in the first, during the first lecture, that once you disorder the system starts to be filled with all the states, and maybe you are measuring not a Majorana peak, but some kind of disorder piling up in the system. And I think the disorder explanation one can exclude because of this, because the wires are very clean, first of all, and second of all, the subband picture, which is kind of very natural for the system, explains, provides some explanation. And third, we know that in some new experiments, one can get rid of this subgap issue quite a bit and have a picture which is, more like this than what they had before. Okay. So then, the other issue that I have to explain is the conductance quantization. So we still need to understand that we still need to understand whether this is a universal effect or not. Okay. And so, in order to do that, I will talk about boundary theories. Boundary theories are actually very important for this question.
Yes. So you said for odd number of subbands, you still have Majorana.
Yes.
What coupling is assumed between these wires?
Coupling?
Yes. What kind of coupling? Because do you assume all the terms that go into the single wire Hamiltonian, or is it a?
Well, I'm assuming that there is some shift. So you have one band, and there is some shift by some quantization for the other subbands, and there is this picture that you have lowest subband number 1, second, third, and so on. And then at some point, when there is a chemical potential, it crosses the odd number of subbands, and that's what I'm assuming.
No, I get it. So those bands are essentially the waveguide modes. I'm saying before you get a solution in terms of waveguide modes, you have multiple wires. And what is the coupling between these wires you have assumed?
Multiple wires? Why? It's one wire, and you just diagonalize for some. So you assume that there is a wire of this shape, right? So you write a model in real space, for example, right? And then you assume that LZ direction, say for example, is very small, so there is just single subband. But this LY direction is not so small, so there are many subbands. And then it's infinite along the X direction, right? So you just solve this problem, and the spectrum will have subbands in real space, and then it's plane waves in this direction, but sines and cosines in this direction. So that's what I'm assuming here. Does it make sense?
Yeah.
Maybe a follow-up on that question. So by different bands, you mean different Landau channels, like
Landau?
Landau channels?
Landauer.
Yeah.
Um,
Of the wire, but so.
Well, Landauer channels. No, it's slightly different. So it's in a different limit. So it's not the metallic limit where you have many channels with the radius roughly determined by lambda Fermi. Here, the quantization effect is important. So there are boundary conditions. And so those boundary conditions, they just, it's like solving a particle in a box problem, and they give you energies, right? Then so that's exactly what I'm doing here. Imagine there is a particle in the box, and you're solving, and then there are states. These are, one node, 0 node, 1 node, 2 nodes, and then there's chemical potential somewhere. So I'll have to, populate the states, and that's the picture I'm using here. So.
And by Majorana band, so basically you have two zero-energy Majorana states.
Yeah, Majorana band is the following, right? So when you solve this problem, you can see from which subbands the predominantly weight is coming in, right? And it turns out that the weight comes from the highest small KF subband. So that's just the result of numerical calculation. One can explain this in some other ways, but that's just, let's take it as some result. And so what I'm saying that in order to see this Majorana, basically you have to lower the barrier quite a bit because it has very low transmission probability. Whereas the other subbands have higher transmission probability, so it's natural that they will leak out more from the semiconductor to a normal metal, and they will hybridize more. And so therefore, this picture, I think, is naturally arising because you have something here, the zero bias peak. In order to see the zero bias peak, you have to lower the barrier, and at that time, these other subbands, they will penetrate through the barrier, they have higher transmission probability, so they might be in this regime where you're not longer measuring the density of states, but it's actually a strong coupling regime where previous calculations, previous conclusions are not applicable anymore.
Sorry, you may have explained it already, but why does it matter if you have an odd number of bands?
If you have even number of bands locally, right? So in the first lecture, I was explaining that there are these two topologically distinct spectra in a vortex, right? So there is a spectrum with even number of levels, and this is a spectrum with odd number of levels. And the robust one is with odd number of levels, right? If you have even number of levels, I can find some perturbation that will hybridize these states and split them off, right? But if I have odd numbers, this level cannot move up or down because it's constrained by the particle Hall symmetry, which tells you that if you move this level up, there should be a partner somewhere down, unless it's at zero energy. So therefore, there is another way. If you recall, I also mentioned that Dirac fermion can be written as a superposition of Majorana fermions, right? Majorana operators. So in some sense, two Majorana operators can give rise to some Dirac mode, and that's no longer Majorana. Okay, does it make sense?
When you say that you need a clean enough wire, is there an estimate how clean this?
Yes, so that was, again, during the first lecture, I was saying that 1 over tau should be smaller, right, than delta. So that's the estimate.
What does SM stand for again? What does SM stand for?
Oh, semiconductor wire. Okay, so let me just go now and try to explain the quantization aspect. So one important and very useful concept is the concept of boundary field theory. So this concept happens when you have some trivial bulk and nothing happens in the bulk, but something interesting happens at the boundary. And that's actually the case in the present situation. So therefore, what one can do, one can just start with this model. So I have two Majoranas. This is my topological superconductor, and this is my wire. And let's for a second assume that this wire is infinite. And remember, in 1D, I can explain interacting wires in terms of this Lutchyn model. Right? So I can bosonize and write down Lutchyn model, and this Lutchyn model is quadratic, therefore I can solve the quadratic problem. So so I do that. I start with all of this, and then I just integrate out all the degrees of freedom except for the one that is here at x equal to 0. Because nothing happens in the bulk, and the only action is happening in the boundary, therefore I will do that. And then I will obtain boundary field theory. Okay. So that's exactly what I'm doing here. I have Lutchyn liquid, and then I have this boundary term, and that's a term that explains what happens at this point. And then I will bosonize two processes, one corresponding to this Andreev reflection, so quasi-particle as an electron is reflected as a whole, and then the normal scattering process when electron just bounces back. And it turns out that if I bosonize, I will have two terms, so lambda m cosine theta and lambda n cosine 2 phi. So this is electron backscattering, and this is basically coupling to Majorana, which will give rise to this Andrea reflection. Okay. So, and then what you can do, you can start with these, when these terms are very small, lambda m and lambda n very small, so we basically take two separate systems and then just glue them together a little bit and see whether where the theory will flow. Okay, so then we will do renormalization group calculation for these couplings and see whether these couplings, they go down or go up. Well, this kind of approach has been known for a while and been known from Lutchyn liquids and impurities in Lutchyn liquids. That's exactly what you would do in this case. And this problem can be also viewed as some kind of impurity in the Lutchyn liquid. So I can take the mode coming in and take the mode coming out, and then I unfold the wire. So I just rewrite, I do a mathematical trick, it's called unfolding. So I'll represent as the mode coming in and the mode that is coming back as the mode that's sort of propagating forward. Okay? And then these terms right here, they will be just the terms that represent some complicated impurity. So very often you will hear this impurity model. So then you do this analysis for impurity model, and this is what you see. So when we cut off the system into pieces, right, then Lutchyn liquid will have just normal boundary conditions. So everything that comes in, so right mover is completely reflected as a left mover, right? That's what normal boundary condition gives you. So we are starting with this perfect normal reflection fixed point where psi right is equal to psi left. That's our initial state. And then we turn on the couplings and see where the couplings will flow. Well, this is RG flow for these two variables. And you can see that when K is close to 1, right? Because close to 1 means that this is non-interacting system. The Majorana coupling grows, and the normal coupling actually scales down. Okay? So which means that the initial boundary conditions that we started with actually were not correct. Because the system will flow away from these boundary conditions to a new state. And in this new state, I have this, I will have to satisfy these boundary conditions. Okay? And these are the two choices that I was telling you in the scattering matrix formalism. Okay? You can understand the scattering matrix in terms of the boundary conditions for the lead electrons. So superconductor essentially changes the boundary conditions in this normal lead, and therefore gives you a different transport properties when you go to lower and lower energies. And that's what happens here. Actually, this is the phase diagram. So for fairly modest interactions, repulsive interactions, which is, I think, a reasonable thing to assume, the prediction is that the system flows to this perfect Andrea reflection fixed point, which is characterized by this boundary condition. And one can show that these boundary conditions exactly correspond to the this resonant Andrea reflection process.
Maybe a nice question. So in the model that you wrote down in the previous slide, what is specific of having a topological superconductor there? I mean, could you have rewritten this same model for a trivial superconductor? Or
Yeah, but then you wouldn't have this term. You would have cosine 2 theta.
Okay. That's it.
So this is the specialty of this system, that you have cosine theta, and that actually changes phase diagram quite a bit, right? So if I had a normal non-topological superconductor, then the transition point would have been here at 1. And then if I had a little bit, so I would just have to move this point to here to 1. And then a little bit repulsive interaction will destabilize the this superconducting coupling, will scale it down. So at the end of the day, you would expect that normal boundary conditions would be stable. But having Majorana actually changes quite a bit. So there is a big difference between topological and non-topological superconductor. Okay, so now once we know this RG flow and boundary conditions, we can try to understand the conductance, okay? And the way to understand the conductance is to do the following. So first, if you want to understand what happens at high temperatures and voltage, we start with these boundary conditions, and then we perturb in relevant operators, and then our perturbation theory will be valid to some cutoff, but we will obtain the high temperature, high voltage behavior. If we are interested in low energy properties, low temperature, low voltage, we start with these boundary conditions and perturb in the irrelevant operator, and then we will obtain the temperature and voltage dependencies. Okay, and that's what I'm showing here. We can obtain, some answer in this region. We can obtain some answer in this region, and then we just have to interpolate between the two. So let's see. Another important aspect for this problem is that the wire is finite, and then there is a normal lead. A normal lead should be considered as a non-interacting problem. So K will be equal to 1. So essentially, this model is a little bit complicated because now Lutchyn parameter will change as a function of space. But nevertheless, there are ways of solving this problem, and there are ways of obtaining the answers. I'm not going to discuss them, but if you are interested, just ask me later. Okay, so I'm just going to give you answers here, and these answers they remind us, in this particular limit, they remind non-interacting case. The only difference is where this K is the K that corresponds to the wire, and that happens for long wires, or K that corresponds to the lead, which happens to the short wires. And here's the deal. The thing is, where is the most of the scattering happens? Is the scattering happens in the short wire, and most of it happens in the lead, or if the wire is very long, most of it happens in the wire, and then the lead is sort of irrelevant. Okay, and that's where you get these two asymptotes. So I can do the same calculation in the other limit, and this calculation actually gives some interesting result. So we get this RG equation, right? And then we perturb and we find the answer. And RG equation just gives us a flow as we go from higher energies to low energies, right? So normally you would expect that whether it's voltage or temperature, it shouldn't really matter, that the scaling of these two quantities will be the same. But remember, I gave you also non-interacting results, and non-interacting results, which we can obtain exactly, they actually gave you different answers. So conductance as a function of temperature in this limit was 1 over T, and conductance as a function of voltage was 1 over V squared. So the non-interacting results seem to tell you that, well, they should scale in a different way, but the scaling analysis tells you that they should scale in the same way. So where is the catch? Well, the catch is that, well, in this case, one has certain coincidental result. That, if you do exact calculation, perturbation theory, what you find that actually the coefficients, it's true, the scaling functions are the same, but certain coefficients up front, they vanish. So this coefficient is finite, but this coefficient F2, when we compute the voltage dependence, actually vanishes. And so it means that we have to go to higher order, and you have to consider 1 over V squared sort of terms. And this way, we kind of reconcile between non-interacting results and the scaling theory. But this tells you that once we turn on interactions, once the K parameter is slightly different from 1, then the scaling theory will give the prediction that, well, dependence on voltage will be very different from what the non-interacting result was, what we obtained from non-interacting calculations. So basically, this is very interesting coincidence that at K equal to 1 in non-interacting limit, one finds that the voltage dependence, so the leading order term, the voltage dependence vanishes. But this calculation is more general and allows you to take into account interactions. And interactions results modify this quite a bit. But bottom line is actually that, well, this quantization in terms of 2e squared over h is indeed a very robust effect. It's independent of interactions, and it's a signature of the boundary conditions. So basically, there's perfect Andreev reflection. The probability resonant Andreev reflection can be casted in the language of this Andreev boundary condition for the lead electrons. And once you cast it in that language, you know that this is very robust. And we would expect to see a quantization of the conductance in the future. So, once they fix the soft gap issue, then they should go back, the experimentally should go back and measure this quantization. And once they prove that it's quantized in 2e squared over h, we will have a better confidence that this is indeed Majorana. So let me just stop for questions here.
Can you go back to the model?
Yeah, so in this model, your topological superconductor is also seems to appear only at x equal to 0, the boundary term. But according to your picture, you have like extended proximity with the.
It's gapped. So I'm assuming the superconductor is gapped, right? And then once the system is gapped, I can integrate out everything except for 0. So that's what I'm doing here as well. I mean, that actually, I was doing this for, when I presented this Andreev reflection. So there are many ways of looking into the Andreev reflection. One way is to just integrate out gap degrees of freedom, assuming that you are interested in low energy physics. You're always allowed to do that.
So this problem is just like a single mathematical wire with an impurity at some point.
Yes. And that's, I think, the power of this calculation, that once you map this problem into the impurity problem, then you can, there are techniques developed in the literature. You can do RG, you can do some other methods, which will allow you to understand what's happening in the system. Okay, so another important aspect that I wanted to cover today is the Kondo effect. Okay. So, as Ali mentioned yesterday, that, well, there is this region here, and very often in this region you might have coincidental formation of a quantum dot. And whenever you have a quantum dot, then one has to worry whether whether this is a Kondo physics or Majorana physics. So you have to understand what happens in the system. But I think, in addition to being some unintentionally created quantum dot, it's an interesting theoretical problem because we know that there are two different ground states to which the system will flow. There's a Kondo ground state, and there is a Majorana ground state, which corresponds to these boundary conditions where psi right is equal to psi left dagger. So you would like to understand the competition, the interplay between these two different ground states, and see whether they coexist or whether they compete and what happens in the system. So I'm imagining that, for example, a system is like that, the normal lead, there's quantum dot, and there's this topological superconductor. And in addition to being nanowire, actually it also can be a Majorana that appears in topological insulators, right? So as I mentioned in the second talk, we can imagine that there is some quantum spin hole, there is an edge, there is a superconductor here, there is a magnetic insulator here, and at this domain wall there will be Majorana, and now imagine that this Majorana is coupled to my quantum dot, and there is the same physics essentially. So in order to study this physics, I will actually use this model, and I will write the Hamiltonian for this model. So I have, again, tunneling between Majorana at the end and electrons in the quantum dot. And so since in the previous model I have some magnetic insulator, it picks the axis along which the spin is polarized. So I pick this axis to be up. And then there is a quantum dot with some level, on-site charged energy, and tunneling between the quantum dot and normal lead. So that's, without this coupling lambda, that would be a standard initial point for a Kondo problem. And now the only thing that I've added is this coupling to Majorana mode. So let's try to understand what happens in the system. But let's first review let's try to understand the low energy Hamiltonian for this problem. So again, what one is doing, in studying Kondo problem, one is trying to project the system from some to some low energy subspace, and this projection is called Schrieffer-Wolff transformation. So one essentially integrates out these high energy degrees of freedom and obtains the following problem. So if I just had the Kondo problem, then I would just have S coupling, the coupling on the dot with the coupling on the spin on the left side of the normal lead. But now, in addition to this Kondo coupling, I will have a few other couplings, and so there is so-called direct coupling. So there is, first of all, induced Zeeman splitting, and that's just tunneling from this magnetic insulator. It's effect of magnetic insulator on the quantum dot. So there is some induced exchange. And then effectively there is also tunneling of a Majorana, which is polarized in up direction, into through some virtual state in the dot to the lead. So there is this coupling. And then there is additional coupling where Majorana basically couples to the spin, and it can flip the spin and then tunnels into a spin down electron in the lead. So there are these all sorts of processes in the system, but I will just try to explain their physics. Let's start with just Kondo physics, and let me just neglect these two Hamiltonians. And by the way, there is a so-called particle hole symmetric point where this psi minus is equal to 0, so which essentially means that 1 over epsilon is equal to 1 over u minus epsilon. And in this point, it's a very special point which I will discuss later. So let's just keep in mind. So Kondo effect. Well, this is the typical picture for a Kondo effect. You have two leads, and you're driving current from one to another. So what happens in the Kondo regime is that the spectral weight gets redistributed, and at zero energy, or at the chemical potential, there will be a peak Kondo resonance with the widths of the order of given by this Kondo temperature T0. And if one tunes the parameters in a particular way, then there will be also perfect sort of transmission through the structure. And it turns out that in this limit, in this unitary limit where there's perfect transmission through the structure, conductance will be also equal to 2e squared over h. So it's so one really needs to consider these two effects and distinguish between them, because they both can give you 2e squared over h conductance. So, but however, if you carefully look at the Kondo physics, it actually gives different boundary conditions. So you see boundary conditions in this unitary limit where there is 2e squared over h conductance, they correspond to scattering shift delta equal to pi over 2. So when scattering shift is equal to pi over 2, that means there is no reflection, right? So if you solve impurity problem and you find the scattering shift is equal to pi over 2, that means there is no reflection, there is just complete transmission. And so these conditions are very different from the Majorana boundary conditions, because here psi right will be equal to minus psi left, whereas in the other case psi right is equal to psi left dagger. So so these are very different ground states, and they do not coexist. Now, let me explain this other ground state. So imagine I tune the system to this particle Hall symmetric point, and then I turn off Kondo, and I try to look at this Hamiltonian. Well, first of all, this Hamiltonian has this additional symmetry. It's anti-unitary symmetry, which is comprised of charge conjugation, C, and complex conjugation. So charge conjugation takes an operator psi and turns it into psi dagger, and complex conjugation is clear what it's doing, right? So it does remind a little bit time reversal symmetry, because if you act on the spin on the dot, it changes the sign, and therefore the spin on the dot, the expectation value for the spin on the dot is equal to 0. So what I'm trying to say that even though the magnetic insulator breaks time reversal symmetry, at that particular point, there is some cancellation of these time reversal symmetry effects, and essentially spin is not polarized and is fluctuating quite a bit. And these fluctuations, as you can see, they remind a coupling of a spin to a fermionic parity. So I have a gamma operator, and I can represent this combination psi up plus psi up dagger as a fermionic parity, because psi plus psi dagger corresponds to Majorana mode, right? And two Majoranas give us fermionic parity. So it's as if the system forms a singlet state between the spin and fermion parity. And in the case of Kondo, the system wants to form a singlet between the spin on the dot and the spin in the lead. Whereas here, it's a spin on the dot and fermionic parity shared between the lead and Majorana. Okay. It turns out that this problem can actually be solved exactly by introducing some new Majorana operators which satisfies the same algebra, and therefore the mapping is exact. However, in terms of these new operators, this Hamiltonian becomes just fermion bilinear, and so one can compute all the correlation functions. And in fact, one finds that conductance is indeed equal to 2 squared h, but the boundary condition is the following. So you have a tensor product of Andreev times normal boundary conditions. So it's Andreev for spin up electron. So for spin up electron, we have psi right is equal to psi left dagger, whereas for spin down electron, we have psi right is equal to psi left. So therefore, you can understand this result as if spin up electrons in the lead, they are just getting this resonant Andreev reflection, whereas spin down electrons are completely reflected back, and they are not transmitted at all through the structure. So that happens, that only happens at the particle Hall symmetric point. An important distinction is that spin, once we tune away from this particle Hall symmetric point, that this symmetry is no longer present, and the spin will get polarized. So that gives us a very interesting effect that as we tune away from the spin from this particle Hall symmetric point, the spin will stop fluctuating. It will freeze out at some point. Whereas in the Kondo effect, particle Hall symmetric point is not any different from any other point. So spin is still fluctuating, and time reversal symmetry is preserved. So it's a very specific prediction. As you tune away from this point, and you measure, say, derivatives, the slope dsz, for example, with respect to the gate voltage, that there will be very different dependence. There will be very strong dependence on gate voltage in the case when you have Majorana, and there will be very weak dependence in the case when you don't have Majorana. And so to understand, we did density metrics anonymization group analysis with this problem. We also have some exact analytical calculations, and they match up very nicely here. But the point, so what's plotted here is this quantity as a function of the Majorana coupling, and this line corresponds to no Kondo, and then the Kondo coupling is increasing in this direction. And so eventually when the Kondo coupling is very large, this line will become flat. And that means, that tells you that, well, the Kondo effect is insensitive to this point, so spin fluctuations are not affected. But in this limit, you see that there is a very strong dependence on that. So that's one of the predictions for this model. That if one can measure somehow spin fluctuations on the dot, then one should be able to distinguish from Majorana and Kondo physics. Another technique that is very useful for this problem, and I'll just flesh out results, is the so-called slave boson approximation. So you can just take complete model and use the slave boson mean field approximation, find the right mean field value, and obtain results. And again, ask me if you want to know details, but I'll just tell you the results here, that in the case where there is no splitting between the two Majoranas, so now I can, within this model, I can add the splitting in this topological superconductor. And if the splitting is large enough, right, then there is a large gap, then it's as if we don't have any Majoranas anymore. Whereas when the splitting is small, it's like, we still have this gap. So, so in the case when we don't have any splitting, the prediction is that we have zero bias peak, and the Kondo resonance is split by this induced exchange. Whereas if we increase the Majorana splitting, the picture changes quite a bit. We don't have any zero bias peak anymore, and we just have two peaks, and this is split by and this is essentially magnetic field induced splitting of the Majorana modes. Okay, I think I'm running out of time, but I spent too much time on zero bias tunneling conductance. But the point is that one should be able to distinguish between Kondo effect and Majorana effect in these experiments, and we have tons of predictions how one can do that. And it seems unlikely that in these Cohen-Cohen's experiment, Kondo effect can arise at such a large magnetic fields. Now, another interesting effect is a fractional AC-Josephson effect. And this fractional AC-Josephson effect corresponds to some very interesting dependence of the Andreev spectrum. So what one does in this problem, it just studies the S and S structure. So you have one superconductor here, you have another superconductor here, and you have sort of like a normal region in the middle, which corresponds to this nanowire. And so one looks for the presence of the bound states in this region. And depending on the phase difference between these two superconductors, these bound states, they will have different energy. And so in the topological phase, the dependence of these bound states on energy is cosine phi over 2. Whereas in non-topological state, actually is very different. So this is a simulation. As we change Zeeman coupling across the phase transition, one can see that the spectrum changes quite a bit. So this spectrum is 2 pi periodic, as you can see here. So all the lines, if you follow the line, it just comes back to the same value. Whereas the spectrum in topological phase, you start here and you go down, or if you start at 0, you go up and end up with 2 pi. And that's this cosine phi over 2 effect. So this should be visible in the Josephson current. So if I take a derivative of the spectrum with respect to the phase, that's proportional to the supercurrent that is flowing through the structure. And therefore, I should be able to distinguish, because one of them will be in the maximum, and that's these two, whereas the other one, these two are at the maximum, whereas the conventional dependence, which is 2 pi periodic, will be at the minimum. So finally, I wanted to mention that, well, even though we have this cosine phi over 2 dependence, we it's important to do this measurement, AC measurement, rather than DC measurement. So if we include some relaxation mechanisms into the picture, then the temperature average current actually is a product of the I phi and this function. And as you probably can see in this movie, that the particle follows, but then relaxes and comes back to the state. So if we are doing some kind of DC measurement, one would still see 2 pi periodic effect, whereas if we do an AC measurement, then we don't see, we will be able to distinguish. So here's one way of doing this. It's some kind of a design where one measures the impedance of the circuit in time domain. And so from some tiny shifts in the impedance of the circuit, one is able to detect whether the system has this anomalous Josephson effect or no. So, so that's. So let me just explain this signature here, and I think I should probably. How much time do I have? Actually?
You already run out of time for 5 minutes.
For 5 minutes. Okay, I started a little bit late, so let me just flash 2 slides and I'll stop. So another effect which is very important is this interferometry effect. It turns out that this effect allows us to do the measurements, non-local measurements. And there is Aharonov bomb effect, where if you take a charge around the flux, right, there is some Aharonov bomb phase. But there is also Aharonov-Kasher effect, which is dual to Aharonov bomb effect, so, which tells you that if you take a flux around the charge, there will be also some phase picked up, right? So in these Josephson experiments, what happens in this flux qubit type of experiments, what happens is that there are fluxes tunneling through the junctions. And it turns out that in this case, there will be dependence on the charge enclosed in this region. So if I imagine this fluxon tunneling around the loop, this fluxon will pick up the phase, which is so-called Aharonov-Kasher phase. And this phase will be sensitive to the effective charge in this enclosed region, and this effective charge will depend on the fermion parity of the Majorana wire. And this fermion parity of the Majorana wire, and so by doing this measurement, we can measure the combined fermion parity of the network of the wires. Okay, so this is the slide that I'll just flash. So if we take these wires and we make network of these wires, then we will be able to manipulate the position of these Majoranas. So we can just change the regions where the wire is topological and non-topological, and we can move them around in the network of the wires. And then this flux interferometer allows us to create the devices which are called topological quantum buses. And these buses, they allow one to couple topological qubits and conventional qubits. And by coupling these topological qubits and conventional qubits, we'll be able to teleport this missing gate to the structure. And we will be able to complete these braiding gates, the topologically protected gates, with some, just a single, it turns out, the single non-topological gate. And that would make all these schemes universal. So that's the idea. I was supposed to cover more, but there were many questions, so I'll stop here. And if there are very few questions, maybe one can.
Since we already ran out of time a lot, maybe if you have some questions,
maybe after.
Ask Roman personally during the break. And let's thank the speaker again. Thank you, Roman, for giving us lectures here, and that's a small gift for you. Okay, thank you. Okay, let's come back and share the whole talk.